Hi guys. So in the last video, I left you off with this question. Find a function f such that the integral from 0 to infinity of f of x dx converges, but the integral from 0 to infinity of f of x squared diverges. So at this point, I'm going to ask you to pause the video and see if you can come up with a function that satisfies these conditions, and then see if that function matches the function that I'm going to show over here. So hopefully by now you paused the video and attempted this question on your own. Now the first thing that I want to emphasize over here is that if you are using some sort of a triangle, a function f of x that has some triangular peaks, it's usually not going to work, especially if the height of the function that you've picked is constant. And here's why. Uh, the reason why it won't work is actually quite simple. Let's say you have a function that looks something like this. So there are triangular peaks at every integer, and you said that the height is constant. Now, what's going to happen is, let's say that this is your function, and let's assume that the integral from 0 to infinity of f of x dx converges. One possible case is if you let this height to be 1 over n squared, then the integral from 0 to infinity, if you keep on drawing these triangles, the integral from 0 to infinity of f of x dx will just be pi squared over 12. So it will work out. But the issue is that you also need to make sure that its square diverges. And when you square such a function, you're gonna get this straight line over here, this straight line over here is going to bend inwards, something like this. And the issue is, there are two issues. First of all, even if you are able to come up with a function where where f of x squared diverges using triangles, there's no way to bound such a triangle, or no neat way to compute. This isn't even a triangle, but there is no neat way to compute what the area is underneath this graph and show that this area diverges. But the second and perhaps the more important issue in this case is that the area underneath the graph of the square, is clearly smaller than the area under the graph of f of x. So, well, if the area under the graph of f of x converges, it's finite, then the area under the graph of f of x square must also converge. It's also going to be finite. The moral over here is that although you might be able to come up with a function with triangular peaks that satisfies these conditions, in general, it is preferred to stay away from triangular peaks, and instead I'm going to use trapezoids or trapeziums. So this is how I'm going to define my function. I'm going to say that at every peak, let's say this is 1, 2, 3, and 4. So I'm going to say at every integer n, my function f has a trapezoid or a trapezium, same thing, with the following properties. So number one, the height of the trapezoid. So I have to state the height. The height of the trapezoid is going to be n. Number two, the length of the bottom base is going to be, well, let's say 1 over n cube. And the height of the top base is going to be 1/2 n cube. So something like this. Now, just to give you a little bit of a visual idea about how this will look like. So let's say at 1, it's probably going to look something like this, where this height is 1. So this is 1, that's it, this is 2. At 2, it's going to look something like this. Well, it's going to become a trapezium that is very, very thin. So it's going to become something like this. Okay. And then it's going to continue going on like this. So let's, and of course, the last property is that f is 0 everywhere else. So everywhere in between those trapezoids, f is just 0. Everywhere else. So let's see what the integral from 0 to infinity of f of x dx is. Well, this is just the same thing. Well, the integral essentially just computes the area under the graph, and that can just be written as something like this from n equals 1 to infinity of a sub n, where a sub n is the area under each one of these trapezoids. And this is just going to be the same thing as n equals 1 to infinity, while the area of a trapezoid is 1/2 times the sum of parallel sides. That's just the sum of 1 over n cube plus 1/2 n cube, which is just 3/2 n cube. So 3 over 2 n cube. And multiplied by the height of the trapezoid, which is just n. And if you simplify this, you're going to get 3 times 3 over 4 times the summation from n equals 1 to infinity of 1 over n squared. And at this point, you're going to conclude that this converges because the summation from n equals 1 to infinity of 1 over n squared is a convergent series. Or if you want to be more precise, you can say that, well, this is just equal to pi squared over 6. And this is just equal to pi squared over 8. Once again, this follows from the Euler's identity. The summation from n equals 1 to infinity of 1 over n squared is pi squared over 6. So clearly, the integral from 0 to infinity of f of x dx converges. But now let's look at probably what is the harder of the two integrals, the integral of the square of f of x squared dx. Now the issue is quite simple. There is actually no direct way that you might be able to come up with some direct way to compute what the integral from 0 to infinity of f of x squared dx is. But I'm not going to do that. I'm going to show you a rather simpler way to do it. Notice that I only want to show that the integral from 0 to infinity of f of x squared diverges. I do not want to know what its exact value is. So in this case, let's look at just one of these trapezoids and let's see what's going to happen. So I'm going to look at this trapezoid. Now, when I square it, it's going to look something like this. Since the height is 1, it's going to remain 1. If the height was 2, it was going to change to 4 because, well, you're squaring the function. So every value is just going to get squared. So this is a straight line. And if you square it, it's going to become something like this. If you square every value, it's going to become something like this. Same thing is going to happen over here. And this is just going to remain a straight line. If you look at this trapezoid, well, this one is it's a little bit hard to draw. But what's going to happen is, let's say that this is 4. It's going to become something like this. Well, it's going to become a curved line that's going to look something like this. And then it's just going to be a straight line over here. But the fundamental idea over here is that at each one of these trapezoids or trapeziums, what you can do is you can bound the area under the graph of f of x by the area of this rectangle. In other words, the area of these rectangles in each one of these trapezoids is always going to be less than the area it's always going to be less than the area which is bounded by f of x squared. And now what's going to happen is something like this. So what I'm going to say is, or what I'm going to state over here, is that the area of each one of these rectangles, so let's say that's the same thing as the summation from n equals 1 to infinity of, let's say, b sub n, where this is where n equals 1 to infinity of b sub n is just the area under the sum of the area under each one of these rectangles. This has to be less than the integral from 0 to infinity of f of x square dx. And I'm going to show that this summation diverges to infinity. And if this diverges to infinity, since this must be less than the integral from 0 to infinity of f of x squared dx, this integral must also equal infinity, or must also go to infinity. Or in other words, it must diverge. So, well, let's look at what happens to this. So this is just the summation from n equals 1 to infinity of b sub n. This is just the the area of each one of these rectangles. So what's the area of the nth rectangle, where b sub n, of course, represents the area of the nth rectangle. So the area of the nth rectangle is quite simple. The height of each one of these rectangles is n squared, because, well, the height of the trapezium was n, and now when we are squaring it, the height is going to become n square. So let's just put that down, n square. And this length over here, the length of the rectangle, is just going to be the length of the top base in each of these trapezoids. The length of the rectangle is simply the length of the base, of the top base. which in this case is 1 over 2n cube. So you just multiply this by 1 whole over 2n cube. And if you simplify this, you're just going to get the summation from n equals 1 to infinity of 1 over 2n, which can be written as 1/2 times the summation from n equals 1 to infinity of 1 over n. And this is, of course, the harmonic series. This diverges to infinity, and 1/2 times the harmonic series must also diverge to infinity. You can use the basic comparison test or the limit comparison test to be a little bit more rigorous, but at this point you can actually conclude that this diverges to infinity. So this has to diverge to infinity. But then since this diverges to infinity by the basic comparison test, as this diverges to infinity by, you could write down by the basic comparison test, as 0 is less than the summation from n equals 1 to infinity of p sub n, which is less than the integral from 0 to infinity of f of x squared dx. And because the summation from n equals 1 to infinity of p sub n diverges to infinity, the integral from 0 to infinity of f of x squared dx must also diverge to infinity. And this will complete the proof. So the idea behind this question is quite simple. To find a function such that the integral from 0 to infinity of f of x converges, that is very, very simple. It's harder to come up with it's harder to prove that the square of that function will also that the square of that function will diverge. But this is the idea about this is the idea you go about when you're solving such questions. You don't need to explicitly compute what the area under the square is going to be. You just need to bound the area. You just need to bound the area of f of x squared by something that has a smaller area, and then show that that smaller area diverges, and thus conclude that the integral of f of x squared must also diverge. And yep, that will be all. I hope you enjoyed the video, and I'll see you in the next video.